as you just heard, my name's Kathy Whaler. I'm Professor of Geophysics at the University of Edinburgh. Let me start off with a bit of career trajectory. I was at Croydon High School. I left in 1974 with A-levels in physics, pure and applied mathematics, and geography. And from there, I went down south to University of Sussex, just outside of Brighton, where I started off taking a degree in physics, but soon realised that I wasn't actually very good in the lab. So you're all working in the lab today, and that would not have been my forte. So I switched instead to doing mathematical physics, which basically meant I did a lot more maths and I dropped all the labs, which actually suited me incredibly well and has been a very good foundation for my subsequent career. So I loved physics as an undergraduate, but I felt there were rather limited options as to what you could do as a postgraduate in physics. There were lots of opportunities, opportunities to places like CERN and things like that. And while I loved modern physics, I just thought, no, I want to be more of a lone player rather than a super big team player like you've got in projects like CERN. So I thought back, well, I've got geography, that told me something about the Earth, so why don't I do a PhD in geophysics? And so I went to Cambridge and I was there for just over 3 years, getting on for 4 years by the time I submitted my PhD. And I'll tell you a little bit more about the kind of work that I've been doing research-wise in a couple of later slides. I stayed on in Cambridge for a couple of years after I finished my PhD, devoted full-time to research, but those kind of opportunities are only usually fixed term. So after that, you have to think about getting a proper job. And I thought, well, I better start thinking about trying to get a proper job. And an opportunity at the University of Leeds came up. So I thought, well, that will be good practice for writing my CV. And then I got an interview and I thought, oh, well, that'd be good practice for getting an interview. And then I got offered the job, which I decided to take. So I was at University of Leeds for years as a sciences. And then in 1994, I moved to Edinburgh, where I've been ever since as Professor of Geophysics. So that's my career trajectory. Along the way, I've had some fantastic opportunities for research visits and sabbaticals at super interesting places too, both for work and for, just to be in a different environment. So one was at Scripps Institute, or a couple of times I've been to Scripps Institution of Oceanography, which is near San Diego in Southern California. I've been to the University of Colorado at Boulder a few times. I spent a few months at Harvard University. I went to one of the NASA institutes, Goddard Space Flight Center, which is just outside of Washington, D.C. in Maryland. Göttingen University in Germany, which is the birthplace of one of my heroes, Carl Friedrich Gauss, and Victoria University of Wellington in New Zealand. So, and some of those have been associated with collaborations, obviously, with other people or with fieldwork. So I thought I'd try and give a very brief summary of my research interests, and there's two bits to it, and they're kind of interlinked, but not obviously so, and I can go into that details later if anybody's interested. So my first basic area of research was to try to understand the origin of our geomagnetic field, the magnetic field that means that our compass needles point more or less north. And that's caused by processes taking place in the very deep interior of the Earth. So what I do is I look at measurements of the changing magnetic field components. I'm sure you know that the magnetic field is a vector, so you need to describe it by observations of 3 components if you're going to look at the full story. And I use measurements made at and near, from satellites, as I'll talk about a little bit later, the Earth's surface. And from that, what we can do is to infer the convective or the overturning flow of liquid iron in the outer core. and I'll show you a snapshot through the core in a moment, that generates the geomagnetic field. And this is a process that's known as the geodynamo. And it's been a huge area of interest for research for many, many decades as people have tried to understand what's going on. And partly because of what I did in my first visit to Scripps Institution of Oceanography, I also got interested in the electrical resistivity. So this is how well rocks conduct electric currents in the crust and the upper mantle. And again, I'll show you a snapshot through the Earth, which I'm sure you already know about in a moment. And the way I do that is by measuring tiny time variations of the electric and magnetic fields. And those changes are driven by interactions between the solar wind and the Earth's magnetic field. So they're taking place on quite rapid timescales. And from those, you can infer the strength of and geometry of the induced subsurface electric currents, the electric currents that flow in the interior as a result of that. And from that, you can then deduce how conductive the rocks are. So this is the basic Earth structure that maybe I should have put on a little bit earlier, that you're probably fully aware of. So in my the bit I've just been talking about, I've been looking at the crust and the rigid mantle. So maybe the top 50, perhaps 100 or so kilometers of the subsurface. And then in the first part I was talking about, I'm looking at the liquid outer core. And in between, we've got a stiff but able to creep mantle that's made of silicate minerals. And then we've got a very, very strong compositional change when we go into the iron nickel dominated core. And basically what happens is, obviously, as you go down, you're getting hotter and hotter, but you're also getting higher and higher pressures. And in the outer core, temperature wins over pressure, so it's a liquid. And in the inner core, pressure wins over temperature, so it's a solid, even though it's hotter. Okay, and what we think happens is that the outer core, this liquid iron mixture, overturns and supports the flow of electric currents, and through the changes in those, we generate the observed magnetic field, which we know has existed for millennia, since more or less soon after the Earth formed. And understanding those processes and what it tells us about the composition of the core and when the inner core nucleated and things like that is super interesting to me. So my thesis, the early days, and now I've told you my trajectory, so you know I'm old. Computing power was obviously really, really limited. And what I used was the annual rate of change data from 106 geomagnetic observatories shown on the map here. Okay, and those were manual, in those days, manual observations, you know, made by people who went out and measured things. I mean, there was a certain amount of analog measurements, so they recorded to old tapes and things like that, but obviously the fidelity that you could collect then was very, very limited. And also computers were, you know, tiny. The sort of things that you've got on your phone now are far exceeding what I had available to me then. So my 318 data, really, I had to work hard to work out how I could put them into a computer and work on them in the way I wanted. So that was big data back then. Now, towards the end of my PhD, someone from NASA Goddard Space Flight Center came on sabbatical to Cambridge, and he was working on this satellite shown on the right, which was called MagSat, which was the first time we'd measured the Earth's magnetic field, the full vector information from space. So it collected 7 months of data in 1979 to 1980, and that was really the start of my satellite Earth observation journey. And MagSat was really quite clever because it all folded away for the launch, but you want to measure the magnetic field of the Earth, not the magnetic field of the spacecraft. So it had a 4-meter long boom, which was extended after launch. And this bottom picture here is actually a genuine photo. The top one's a mock-up, but the bottom one's a genuine photo of when they were in some of the lab testing pre-launch. So this was a zero gravity field, just to see how the boom that you can just see here deployed after it was launched. So here's the satellite, and there's the boom extending along the line of sight of the photo there. Because they wanted to make sure that it was going to function, or they wanted to try to make sure it's going to function properly. So I really enjoyed working on some of the MagSat data with the NASA people in subsequent years. And there was actually a really, really long gap after 1980 before we had any more satellite magnetometry. So for about a decade, those were the only satellite data that we had. Okay. Now, if we move forward to what we have available today, things are really quite different. What I'm showing here is an aerial view of Estelmuir Observatory, which has actually been running for a very, very long time, but is now more or less fully automated and collects data at every second. And those data are available in real time. People can check them from the office and so on and so forth, and make sure there's not a problem. Used for all kinds of applications, and I'll mention a couple more later on. And on the right, I've just showing you again these observatory locations. There are more than I used for my thesis, and they are making more or less continuous measurements of our vector components of the magnetic field at these fixed points. Now you can see one of the problems with our observatory network is there's huge gaps over the oceans where there aren't any observatories, and there's far fewer in the southern hemisphere than there are in the northern hemisphere. So they provide fantastic time series of the magnetic field, but there are big spatial gaps. So that's where our satellites come in. And the one that we're particularly working with these days is the Swarm constellation. So since after that 10-year hiatus after MagSat, we've had more or less continuous operation from 3 satellites or 3 satellite missions. And this is the latest ESA mission, Swarm. And you can see it's a constellation. So there's actually 3 satellites simultaneously measuring the magnetic field. And I'll try and play the video on the right here. And you can see this is 1 day's worth of data from one of the satellites. And what we're showing here by the color coding, by the color bar, is the strength of the magnetic field, okay, as measured by one of these satellites. And they're operating at an altitude of a few hundred kilometers above the Earth's surface. And I'll make a comment when this is just about finished about what we see here. Okay, so you can see in 1 day we've got pretty good coverage, and as days go by the satellite orbits drift ever so slightly, so we build up a fantastic spatial picture of the Earth's magnetic field. The SI unit of the field strength is is Teslas, and the useful value is nanoteslas, because the field that's associated with magnetized rocks, if you get a lump of iron or something like that, is a few hundred nanoteslas. So nanoteslas is the number that we tend to use. What I wanted to point out before I move on is this this region of very low strength, okay, of the magnetic field. And this is now known as the South Atlantic anomaly, although it spreads over an area that's much bigger than the South Atlantic. And hopefully I'll remember to make a comment about why that's important a little bit later on. Okay, so the other strand of my research, where I'm trying to probe the electrical resistivity of the shallow subsurface, involves me going out and collecting my own electromagnetic data. So electromagnetic, we want to measure the electric field, and we want to measure the magnetic field. The magnetic field I'm showing the measurements of on the right-hand side here, and these are magnetometers that measure periods up to a few tens of thousands of seconds, which are consisting of many turns of thin wire wound around an iron core. And that it enables us to amplify very, very small signals. And what we do is we use sets of these coils, so they've all got to be accurately leveled. There's a spirit level, oriented carefully north, south, east, west, or vertically. And then we use those to measure the magnetic field changes. And then to measure the electric field, we've got some fancy electrodes. I won't describe them here, but we bury those in the ground, and then we measure the voltage between pairs of them. So again, accurately oriented north, south, and east, west. We measure the separation between the pairs, and we measure the voltage difference between them, and then we can calculate the electric field as the change in voltage over the distance. And then this is us well, it's not actually me, but it's part of our research team in the field, testing the data quality before we leave the instruments to record for a few days. And those provide the data that we use for those particular studies. Now, I've done field work in other parts of the world, but lots of that field work has been taking place in the East African Rift. And I'm guessing you know a little bit about plate tectonics, so you know that we've got a series of fairly rigid plates that meet along boundaries, some of which are what we call convergent, where the plates are moving together, and others are what we call divergent, where they're moving apart, and we're generating new crust. So this is the East African Rift system, where you can see from the arrows here that I'm trying to show that the plates, the African or Somalian plate here and the Nubian plate here, are moving apart at a few millimeters per year. So I've done field work through a lot of places along the East African Rift, and you can see at its northern end we've got what we call a triple junction. This is where three plates are three intersections are happening. So if we go along the Red Sea to the northwest here, we can see the Arabian plate moving away from the Nubian plate. And if we go along the Gulf of Aden here, we can see that the Arabian plate is moving away from the African plate. And the triple junction here is where those three essentially ridges are meeting. And it's the only location on land currently where that's happening. Most of the others, all the others are submarine. And the reason that my method, this technique that I've been using, is super interesting is that in the northern part of the rift, throughout Ethiopia, there's lots and lots of magma in the subsurface. And that enables, or that facilitates, this continental rifting, where eventually we think the plates are going to split apart completely and we're going to have a new ocean formed. So when we write our grant proposals and give talks, we talk about the birth of a new ocean and so on and so forth. The technique is very, very good at looking for magma because it's got a higher electrical conductivity than the solid rock in which it's embedded. So we image it really very easily, or relatively easily using the data collected. And my projects in the East African Rift, most of them have been part of super interesting multi-technique methods. So working using the interpretation of my data along with other data like seismics and geology and geochemistry and so on and so forth. So that's all been great fun. And Afar is just the most amazing place to go and visit. So here are a couple of images from the air. And you can see here how you've got series of blocks that are basically faulted. So the Earth's been dropping down towards the center of the rift here. And this is just like you see the bathymetry of what's happening in the ocean as well. So that's another piece of evidence that this is plate tectonics, triple junction above the Earth's surface, very much like we see below the Earth as we're forming this new ocean. And this is just an example of a volcano with a caldera here. And you can see the topography, and you can see that it's impossible to build roads. So we actually had a helicopter to assist us during the fieldwork for this particular project. Now, you might think, well, okay, that's just all ground data, but actually satellite imagery was really, really useful because we needed little patches of sand so we could bury our equipment, as you've just seen on the previous slide. And most of this is bare rock. So we use spot imagery to find the sandy pockets of about 100 meters diameter, which you can see from space, to deploy our equipment, and then GNSS or GPS to find the sites we identified. So we could give the coordinates to the pilot and he'd drop us down there. And then also we knew exactly where we'd made our measurements. So that's the two strands to my group, my own research. And then I thought I'd say a little bit about other people working with me. So my group at the moment, the numbers go up and down. I've got 4 PhD students and 1 postdoctoral researcher. And 2 of my students are actually working on space weather, which, as you can imagine, is something of a theme. I don't know if you were able to see the aurora where you are over about 2 or 3 weeks ago. Fantastic display, certainly up here. I was in London, so I missed it. Although that's a beautiful thing to see, it's also got consequences. So space weather is one of the things that's on the government's national risk register because it can impact things like the flow, our power system, our train system, and so on and so forth. So IDLIS is making a new electrical conductivity model of Great Britain using the technique I've just described. And that's going to enable us to improve our estimates of the unwanted electric currents that flow in power systems when we've got solar storms happening at times of heightened solar activity. And that work is all done in conjunction with the power suppliers, and then other people working on this kind of stuff work with the train companies and so on and so forth. Now, Sam is using satellite data collected near the sun. So he's basically looking at solar observations, things like the solar wind speed, images of the sun, evidence for solar flares and so on and so forth. And he's trying to harvest all those data and use them to forecast space weather effects at the Earth's surface. So he's trying to work out, okay, now we've got this advanced warning of some solar activity, then can we actually say where on Earth is likely to be impacted, where and when and how? And he's using AI methods a lot to do this. And that, again, should enable stakeholders, as we now call them, to work out how to mitigate the space weather effects. And now Zaina and Frederick are working on the other 2 strands of my research. So Zaina's making measurements of properties of Earth materials, things like iron, nickel mixtures and so on and so forth at super high temperatures. So she zaps her samples with lasers and super high pressures. So she squeezes them, and she does that by applying pressure from the points of diamonds. So tiny, tiny samples that she heats and squeezes. So she's measuring things like the thermal conductivity. How easy is it to conduct heat in these type of materials? Because that's going to have a big impact on how the Earth dynamo works. And Frederick is using geomagnetic data of the types I described, the satellite and the ground data. And he's actually using tiny, tiny changes in the length of the day. So you might think, well, a day's 24 hours. But actually, there's angular momentum exchanges within the Earth system overall. So bits of the Earth slow down, and other bits speed up. And he can use those to, along with the geomagnetic data, to study liquid ion flow in the outer core. And Ashley really got into his computing stuff. So he's building online tools that enable the community to visualize and access the swarm satellite data and the models and products derived from them easily. So there's vast quantities of data these days, and how you get them and what you can do with them and so on and so forth can be very, very complex. So I've said they're models. You can probably work out, those will be, you know, like pictures of the components of the field, for instance, and other things that Swarm measures, but also things like products. And these are indicators of how disturbed the sun is and so on and so forth, or how disturbed the magnetic field is as a result of the sun. So those products are actually of immense practical importance as well, because if you know you've got a solar storm coming, then you know it affects the atmosphere. And so the space agencies will use these indices to decide whether it's safe to launch satellites or not. So they use them as sort of a go, no-go indicator for satellite launch. And if Elon Musk had thought about it, he might have used it before he launched all those Starlink satellites that then got failed to reach orbit, because he launched them during a magnetic storm and the atmosphere was more dense, and so they all deorbited instead of doing what they were supposed to. But that's an aside. Okay, how are we doing for time? Okay, I think so. Space agencies now have launched a huge number of satellites, and you can see the timeline. This is just an old image from ESA going along here, looking into the future, and not very many to start with, and tons now, partly because a lot of the satellites they've launched were so good, they've lasted well beyond their natural life, but also because we're so much better able to measure things from space. So the Earth observation part of ESA has got 3 pillars to it. So there's the meteorology pillar out here with a lot of the Sentinel missions. There's the Copernicus stuff here, again, with Sentinel missions. So a lot of this is recording key Earth variables, providing data that's used for risk and hazard work and so on and so forth. And then the flagship part of the ESA Earth observation part are the Earth Explorers, which are shown here. And these are the big ticket items. And I'll tell you a little bit about how long and what is required to get one of these launched in a moment. But we can also look at, and again, this is a slightly old slide, so it's got wrong dates and things on it, at the Earth Explorers. So I've mentioned already Swarm, which is the one that I use. You probably heard of Cryosat as well, because that's looking particularly at the poles to look at the state of the cryosphere or the ice caps, particularly what's happening in Greenland and Antarctica. And then SMOS is soil moisture and ocean salinity. So that was looking at trying to measure over land soil moisture and over the oceans, how salty the oceans are. GOCHI is the gravity mission. Well, you probably think, well, we know what gravity is. It's 9.81 meters per second, which is true. But if you look in about the 6th decimal place after the 9, there are very, very small changes in the Earth's gravity field, which GOCHI was designed to measure. It was a short-lived mission because it measured really, really close to the Earth's surface to get an incredibly fine-scale resolution model. And then we've got the fluorescence mission, the biomass mission, looking particularly at the, and these are looking at obviously carbon contents and storage and so on and so forth. The EarthCare was successfully launched this week. There's obviously been a bit of a hiatus in ESA launches because they were using a Russian platform for a lot of them. And EarthCare was successfully launched from California by SpaceX just within the last week. And Aeolus is now being followed up by Aeolus 2 because it was so successful as a wind mission. And the Earth Explorers are really, as I said, the big ticket items, but they're also the ones that are supposed to do the new science. They do the proof of concept of new ways of observing, and they keep the European community at the centre, you know, as the forefront of technology and scientific advances in Earth observation from space. So let me just say a little bit about this. I'm sorry these are very wordy slides, but I couldn't think of a good way to put the visuals on in the time I had available. So Earth Explorer missions take way longer even than yours to get to launch. So original to proposal to launch is way over 10 years. Industrial partners, 2 industrial partners are used in the design. So you come up with 2 concepts and then decide on one. Technical teams are assessing and refining the performance of the various instruments, checking that they're going to fit within the launcher. So is the mass okay? Is the volume of the satellite okay? Or the satellites in some cases. They collect data supporting the mission, and I noticed from your timeline that you're going to be doing a little bit of this. So to prove the instruments, so you try and do some kind of ground deployment or airborne deployment of the instruments that you're going to use in space, work out how you're going to calibrate the data, and that's often from airborne, possibly ocean buoys and surveys and field campaigns. And ESA's got this fantastic concept that really took me a while to get my head around when I first heard about it, because they have readiness levels, and they have technical readiness levels, and they have scientific readiness levels. And basically that's just assessing progress, making sure that there's a plan to reach the highest levels of readiness that you need before launch. So there's milestones along the way. And the other thing that ESA does is make sure it keeps within budget. And they have had to cancel missions before now, both the Earth Explorer and sort of what they call the Scout missions, the Cube missions, because of the budget problems. And obviously at the moment, they've got huge problems with launch. Okay, and this might be an interesting thing for you to think about, because before launch, what they have is what they call an end-to-end simulator, and they generate synthetic data. So if you're trying to observe the atmosphere, say, right, what do we want to know about the atmosphere? What parameters are there? What parameter values do you think we have? How do those change when we've got certain effects going on? So you generate synthetic data that you're going to, of the type that you're going to observe, add noise to it, and then try to recover what you put in. And that tells us a lot about the processing and the modeling algorithms. It tells us about the accuracy that's required for the instruments, and also how the satellite must be configured and the observing strategy. And as you can imagine, for these big ticket items, there's huge teams of academics working on the science, both the data processing, the calibration and the modeling before and after launch. And ESA produces, and this is common for satellite, for space agencies, many levels of data. So 0 are what you actually download from what you get from the satellite. What level 1 is after some processing and correction, but still essentially raw data. And then 2 are the final data sets and the products that the science community uses. Okay, so just to wrap up with here, given all that, satellite considerations for you, I was asked to postulate a couple of questions. So you've already made a start on thinking about what pre-launch testing is required, I think. What altitude is your satellite going to fly at? How long will it fly for? What will you measure? I think you're going to be doing spectroscopy, so which set of wavelengths? Are you going to be able to make multiple measurements? If so, how often? And I've already touched on the accuracy required. What kind of accuracy do you hope to get? And what will that be useful for? How are you going to get the data back? What's our budget? Are you going to have solar panels or just a battery that's going to keep it going for a certain amount of time? And all of that's going to influence your final design, which I know you've already started working on individual components. And something that is exercising people a lot in the space agencies now, what's going to happen at the end of your mission? Are you going to create space debris, or are you going to be environmentally conscious and make sure that that doesn't happen? And I've already mentioned about end-to-end simulators. can you do some predictions of the data that you would collect with different atmosphere parameters that might be encountered? And that will give you a sense of the range of accuracy of the data you'll ideally collect, or just to see what the different wavelengths will tell you in terms of atmosphere parameters. Try to relate what you're going to observe to the interesting science parameters. What processing of the data are you going to have to do? And then how are you going to use them to infer something about the atmosphere?